Strategic interactions in multi-level Stackelberg games with non-follower agents and heterogeneous leaders. Many real-world multi-agent systems are shaped by strategic competition over shared congestible resources. Examples arise in transportation, energy, and cloud computing, where agents' decisions interact through congestion and directly affect one another's outcomes. However, capturing these interactions in a realistic way remains a major modeling challenge. To see how this works in practice, let's begin with a simple transportation setting. Consider a network used by both EV and non-EV drivers. All drivers travel through links, and these links act as congestible resources. We call them resource type 1 because they are shared by all vehicles on the network. As congestion on a link increases, that link becomes less attractive, since higher congestion leads to longer travel times. Now, in addition to using these shared links, EV drivers must also access another congestible resource, charging stations. We call these resource type 2. Just like the links, charging stations become less desirable when congestion increases, because users may face longer waiting times and reduced convenience. In this setting, the providers of resource type 2, in this example, charging station owners, make strategic decisions such as pricing, capacity provision, or market entry, while anticipating how users will respond. This transportation example can be generalized to a broader class of networked systems in which providers of resource type 2 make strategic decisions in a coupled congestible environment with heterogeneous users. The standard way to model such interactions is through the Stackelberg framework. In this framework, providers of resource type 2 are treated as leaders, while the agents who use resource type 2 are modeled as followers, who respond selfishly to the leader's decisions. By contrast, the remaining agents, those who use only resource type 1, are usually excluded from the strategic interaction and treated simply as an external source of congestion. As a result, most existing models focus only on agents who directly participate in the leader-follower game. Agents who don't generate revenue for providers are typically represented as background flow or sometimes ignored altogether. However, we refer to these agents as non-followers. The limitation of this simplification is that it can lead to misleading conclusions about profitability, infrastructure deployment, and the intensity of competition in markets where congestion is shared across different user groups. To address this, we introduce a hierarchical Stackelberg framework with three interacting components. First, leaders, who make strategic decisions with different decision horizons and action sets. Second, strategic followers, who participate in market competition and adjust their choices under congestion and leadership actions. And third, non-follower agents, who both shape and respond to congestion without participating in market competition. A second gap in the literature is that leaders are often assumed to be homogeneous. In contrast, we study a heterogeneous leader setting. More specifically, we consider a hierarchical decision problem in which one leader makes a long-term commitment when entering a market with competing leaders who interact mainly through short-term decisions. This long-term commitment shapes follower behavior, affects the competitive responses of incumbents, and ultimately changes congestion across the network. At the same time, non-followers also adapt to congestion. Although they are not strategic market participants, they still jointly determine the equilibrium level of congestion, and that congestion feeds back into the strategic outcomes. Now let us return to the transportation example. In the EV charging setting, a new entrant makes a long-term infrastructure decision by selecting charger locations, while incumbent providers compete through short-term pricing. EV drivers, as followers, choose both routes and charging locations under congestion, balancing travel time, waiting delay, and price. Non-EV drivers, as non-followers, choose routes to avoid congestion, but do not participate in the charging market. Because EV and non-EV drivers share the same network, they jointly generate congestion and respond to it. At the same time, the leaders are heterogeneous. Incumbents possess fixed infrastructure and compete only on price, whereas the entrant decides on both infrastructure placement and pricing. As a result, infrastructure deployment, price competition, and congestion-dependent traffic equilibrium become tightly coupled.